Hey, Algebra 2. So we've been graphing things for a little while. Today we're going to talk about transformations. You know, stretches, shrinks, translations, and reflections. Fun, right? So let's start out with a little bit of review of quadratic functions. Sketch the graph of the three functions f of x equals x squared, g of x equals 2x squared plus 1, and h of x equals 4x squared plus 1. I'll show you right here. If you look at these two equations, that wasn't circled very well. They're the same, right? So if we look at our graphs, we have f of x right here, and then g of x and h of x went up 1. And let's see, that would be a horizontal shrink. I guess g of x would be a horizontal shrink, and h of x would be a vertical stretch. Describe the sequence of transformations that take the graph of f of x equals x squared to g of x equals 2x quantity squared plus 1. So it's a horizontal, horizontal scaling by a factor of 1/2 and a vertical translation up 1. In Algebra 1, we're talking about these horizontal and vertical scales, and we use the word stretches and shrinks, which is why I said that. Horizontal scaling by a factor of 1/2 is a horizontal shrink because it's less than 1. Next, describe the sequence of transformations that takes the graph of f of x equals x squared to the graph of h of x equals 4x squared plus 1. So we have the graph of h is a vertical scale by a factor of 4, even though it looks the same, it's something else is going on, and a vertical translation up 1. Little reminder, when I'm changing inside the parentheses, that's my horizontal scale, and my scale factor is 1 over the number in front of the variable. When I've got the number outside the parentheses, it's a vertical scale, and the factor is the coefficient in front of the variable. Okay, just a little reminder there. Explain why g and h from parts 1 and 2 are equivalent functions. 2x quantity squared plus 1 is equal to 4x squared plus 1. I don't know how else to say that. They're the same because, well, they're the same. All right, describe the sequence of transformations that takes the graph of f of x equals sine x to the graph of g of x equals sine of 2x minus 3. Well, this right here is the vertical shift or translation down 3 units. And the 2x in here, remember I just said when it's inside the parentheses, it's horizontal. Scale, and when it's horizontal, it's 1 over the coefficient for my factor. Cool. Describe the sequence of transformations that takes the graph of f of x equals sine x to the graph of 4 times sine x minus 3. Well, that minus 3 is still going to be the vertical translation or shift down 3. and this number in front is vertical. It's in front of what you're working with, not inside of. So when it's in front, it's a vertical scale by a factor of the coefficient as it is. Explain why g and h from parts b through c are not equivalent functions. Well, because they're not. We had f of x equals sine x. I think the other one was g of x equals sine of, wasn't it 2x? Yep. And h of x is 4 sine x minus 3. I mean, it's a silly question. These aren't the same, therefore they're not the same, right? They don't have the same graphs if you graphed them. If I plugged in numbers, I'd get different answers, etc. All right, so let's explore a little bit. Sketch the graph of f of x equals log base 2 of x by identifying and plotting at least 5 key points. I've already plotted it for us, but let's go ahead and calculate the rest of the numbers. Right here, if I plug in a 1, I'll always get 0 no matter what the base is. Log base 2 of 2 is 1. Log base 4 of 2 is 2, and log base 8 of, log base 2, did I say that backwards with the last one? It's log base 2 of 4 is 2, log base 2 of 8 is 4, is 3. And then go ahead and graph it. So graph this down on your paper so that we can talk about it, right? Before we move on, though, just want to talk about, I don't know, let's grab this one. What does log base 2 of 4 mean? Well, it's 2 to the what power equals 4, right? Where the what power is 2, which is why I put that right there. Why is log base 2 of 1/4 negative? That's another question. Log base 2 of 1/4. Well, if I did 2 to the what power equals 1/4, I need my what power. I need that question mark to be a negative number to get a denominator in an answer, right? That's what flips it to the denominator, is the negative number. Another question. What's our domain? What's our range? Remember, domain is all the x values. If I look at all the x values, okay, all of my x values are all real numbers, but they're all positive. So all real numbers greater than 0. What's my range? Well, I would say my range, if I look at the x-axis or the y-axis, because my range is the output or all the y's, they're all real numbers, right? I can go up and down that y-axis, negative infinity to positive infinity. So little reminders here. All right, like I said, make sure this graph and table is filled out so we can answer some questions on the next few slides. Describe a sequence of transformations that takes the graph of f to the graph of g of x is log base 2 of 8x. So f of x was log base 2 of x, right? So the graph of g is now it's in the inside, so it's always going to be horizontal. And our scale factor is always going to be 1 over the coefficient. Horizontal scale with a factor of 1/8. Describe a sequence of transformations that takes the graph of h of x to 3 plus log base 2 of x. Well, now we're just translating or shifting. And here it's positive, so we're going up. Sorry, it's a positive. A vertical translation. by a factor of, well, not a factor, vertical translation up 3 units because we're positive 3. Cool? Alright, complete the table below for f, g, and h and describe any noticeable patterns. So, reminders. F of x was log base 2 of x, and we already did those, so I'm going to draw those in real quick. G of x was, let's look it up, log base 2 of 8x, and h of x was 3 plus log base 2 of x. Right, so crunch through the g of x numbers. 8x, plug it in, I get 0, 2, 3, you see, yeah, 0, 2, 3, 4, 5, and 6. And crazy, if you crunch these out in your calculator, look what you get. So I just punched it in my calculator in advance so I could write them down quickly for you. You don't have to watch me or listen to me crunch numbers. I'm sure I don't have to point out for each domain value, you get the same range value for g of x and h of x. I graphed them, and as you can see, g of x is also h of x. So go ahead and sketch these in your classwork so that we can talk about them, okay? Pointing out the fact that we talked about g of x when we described the sequence of transformations. G of x was the horizontal scaling by a factor of an eighth, okay? Horizontal scaling by a factor of an eighth. And h of x was the vertical transformation, the shift up 3 units. So use a property of logarithms to show that g and h are equivalent. So these are the steps, all the properties of logarithms we learned in the first half of the unit. So if I write down, let's see, g of x was, log base 2 of 8x. I can mess with that a little bit and say I'm at log base 2 of 8 plus log base 2 of x, right? Well, log base 2 of 8 is 3 plus log base 2 of x. Let's say, let's do this. Log base 2 of 8 is the 2 to the what power equals 8, where what power equals 3. So we see that they are actually equivalent because this right here is h of x. So does the graph of p of x equals log base 2 x over 4? Describe the graph of p of x equals log base 2 x over 4 as a vertical translation of the graph f of x equals log base 2 of x. So we're going to use the properties, the logarithmic properties, to show this, just like we did with part f. So let's mess around with this one a little bit. So log base 2 of x minus log base 2 of 4. Log base 2 of x, this is a 2 to the what power equals 4, so we're at minus 2, right? So there we have it as a vertical translation, down 2 units. Okay, we're going to keep on messing with logarithms, right? Describe the graph of h of x equals 3 plus log 2x as the horizontal scaling. Okay, how does that work? It's a horizontal scaling. H of x equals 3 plus log base 2 of x. I can change 3 back into a logarithm. Log base 2 of 8, because 2 to the what power equals 8. What power equals 3. Log base 2 of 8 plus log base 2 of x. When I have a plus in between two logs, it's really multiplication. Pretty cool. And then do the functions. H of x equals log base 2 of 8 plus log base 2 of x. And k of x equals log base 2, 8 plus x have the same graphs. They shouldn't, because they're not equivalent. Oh goodness, they're not equivalent functions. Okay, log base 2, 8 plus log base 2x. Our rules for logarithms say this is the same as log base 2, 8x, where this right here is not. Even if we evaluate them both at 1, so h of 1 would be 3 plus 0, which is 3. And then if we did k of 1, we'd have log base 2, 1 plus 8, log base 2 of 9, which is a decimal. I don't know that one off the top of my head. So they're not equivalent at all. I missed a part of your classwork, so I wrote it in, and I'll read it. Use properties of exponents to explain why graphs of f of x equals 4 to the x and g of x equals 2 raised to the 2x are identical. Properties of exponents, this is a pretty simple one. This right here is the same as 2 squared to the x, which is the same as 2 to the 2x, which equals 2 to the 2x. So since they're equal, their graphs would function the same, right? So part K, use the properties of exponents to predict what the graphs of g of x equals 4 times 2 to the x and h of x equals 2 raised to the x plus 2 look like compared to one another. Describe the graphs of g and h as transformations of the graph of f of x equals 2 raised to the x. Confirm your prediction by graphing f, g, and h on the same coordinate axis. All right, let's use what we know about properties of exponents. So if I just grab this function right here and mess with it, I've got h of x equals 2 to the x plus 2. That's the same as 2 to the x times 2 squared, correct? That gives me 4 times 2 to the x. So if we have everything on here, g and h are the same, so they would graph the same. But the graph of g is scaled vertically. By a factor of 4. G of x is scaled vertically by a factor of 4, and then h is translated horizontally. Two units left. And we're comparing both of these to the function f of x equals 2 to the x. We're comparing it g to f of x and h to f of x. All right, last sort of learning part of the lesson, and then we'll practice a few. I've got f of x equals 2 to the x, g of x equals 2 to the negative x, and h of x equals 1/2 of x. Graph them on the same coordinate axes. Describe the graphs of g and h as transformations of the graph of f, and then use the properties of exponents to explain why g and h are equivalent. Let's do this one first. Use the properties of exponents to explain why g and h are equivalent. If I look at 1/2 to the x, I can say that that would be 2 to the negative 1 to the x, which equals 2 to the negative x, correct? And that's the same as g. So h of x is here, h of x. And I can change that into 2 to the negative x, which is the same as g of x. They are equivalent. The graph in g of h, they are both reflections. Because they're equivalent, they're both reflections about the vertical axis. And that's what that negative does. Okay, that negative right there makes it a reflection over the vertical axis. Cool? Awesome. All right, listen up for a second. We still have quite a few problems to go through. I've got 2 examples and a few exercises. So the video is a tad bit long. For that, I apologize, but I don't want to skip anything. So take a break, go get yourself a drink of water, okay, walk around the room for a little bit, and then come back and focus back on in. Cool? All right, let's get into it. The general form of a logarithm function is given by f of x equals k plus a log base b of x minus h. You'll recognize some h's and k's from when we did quadratics and transformations. And then I believe we used some similar h's and k's when we did trigonometric functions and graphing. So don't get nervous. This is good. We've done a lot of practicing graphing, logarithms, and exponential functions. So you should be able to apply what you know, and it's going to be awesome. So a, b, k, and h are all real numbers, and b is always going to be positive and not equal to 1, and x minus h has to be greater than or equal to 0. All right? So just a few basic rules of our domain, what we're allowed to plug in. So let's try A. Given g of x equals 3 plus 2 log x minus 2, describe the graph of g as a transformation of the common logarithm function. So let's pick it apart. I know that k equals 3, a equals 2, the base is 10, and h equals 2. Notice h is 2, not negative 2. Okay, common mistake. So the h tells me that we've got a horizontal translation 2 units to the right. This tells me that I've got a vertical scaling, not sailing, by a factor of 2, and a vertical translation 3 units up, and base 10. Cool. Now we should know how to graph it, right? Really basic sketch. I know that my common logarithm without anything looks something like this. Here I want to translate it 2 units right and 3 units up. So I'm going to come over 2 and 3 up, and then a vertical scaling by a factor of 2 means this is going to be just a little more amplified up. But don't trust my drawing. Let's put the actual graph up. Looks just like mine, doesn't it? So this is what, if you threw it into Desmos or on your calculator, this is what it would look like. So I went over 2, what we went up 3, yep, up 3, and a vertical scale of 2. Awesome. All right, the general form of the exponential function is given by f of x equals a times b to the x plus k, where a, b, and k are real numbers, such that b is a positive number not equal to 1. So this is what you need to remember. That's my general form. Those are real numbers, and b can't equal 1. So let's pick this problem apart. I've got g of x equals 3 to the 2x plus 1 minus 2. Let's mess with our exponent rules to get this into proper form. Let's see, what can I do here? 3 to the 2 x times 3 to the 1 minus 2. Let's rearrange these. 3 times 9 to the x minus 2. So here we see a equals 3, b equals 9, and k equals negative 2. Now we can tell what happens, right? Let's see. So I've graphed it on the next slide, but let's answer part B. Hold on. So I just wrote down that, oh, where is it? Looking back. Yep. A was 3, B was 9, K was negative 2. G of x, after I broke it all down, was 3 times 9 to the x minus 2. So describe this. What is it? So the graph of G is a vertical scaling by a factor of 3. And we have a vertical translation down 2, which is that one. We're comparing it to f of x equals 9 to the x, so this tells us that nothing else changes there. Okay, things don't change with the graph itself. We're just going to scale it and translate it down 2. All right, let's look at actually, let's answer part C. Be right back. If I compare it to the function f of x equals 3 to the x, then things are just a tad bit different. How did we get from 3 to the x to 9 to the x? So I have f of x equals 3 to the x. G of x equals 3 times 3 to the 2x minus 2. Comparing this with that, we see it. I just need to know what my factor is right there. So we're going to do a horizontal scaling by a factor of 1/2. Remember, horizontal is always 1 over the constant. And then our vertical scaling of 3, which we already had. And then the translation down. Oops, I forgot the n and down. Not sure why. So vertical scale of factor of 3 is because of that. Vertical scale, or horizontal scale factor of 1/2 is because of that, and there. Cool. Awesome. And the graph shows it. It's harder to see on this one because they're not that different, but in green I have this, and then we compared it to blue. Okay. All right, I have 4 more slides. Okay, now we have the exercises that we're going to practice with just a little bit. Graph each pair of functions by first graphing f and then graphing g by applying transformations of the graph of f. Describe the graph of g as a transformation of the graph of f. I use Desmos because it's an awesome way to graph. But we should be able to just look at this and decide what my transformation is going to be between f and g. Okay, that's how I'm changing it. If I go back to my general form of the log function, a in this problem is 2 and h is 1. So it tells me exactly what's going on, right? This tells me I have a vertical scaling by a factor of 2. And the h tells me horizontal translation 1 unit to the right. Cool. So what we see here in red is that function, and then in blue, so f of x is in red and g of x is in blue. Okay, one more time. Okay, why don't you guys try this one on your own? Okay, write down what the transformation is and check your answer with me. Go ahead and push pause and try it. Okay, the trick here is to get that g of x function to look more similar to the f of x function. And you have to recognize that you can actually take the log of the constant 100. So I split up log 100x into log 100 plus log x. And then I can take the log of 100 and I get 2 plus log x. So now I have something to compare to. So this 2 right here is your translation 2 units up. Okay, let's try this one. I'm going to push pause. You may have to mess with the equations or the functions a little bit to get them to be similar, but check your answer when you're done. Go ahead and push pause. Alright, this one took some manipulation. First of all, this is negative. I bracketed it because I need to split up this log a little bit, and I didn't want to lose this negative. I need to distribute a negative inside the parentheses. Then I realized that 5 times the quantity x plus 2 I can split up. So I took down my parentheses and I have negative log base 5 of 5 minus log base 5 of x plus 2. Log base 5 of 5 is 1, and then I have minus log base 5 of x plus 2. Now let's go ahead and split it up. This minus 1 right here, this negative 1, means I'm translating down 1. I didn't write translating. Translating down 1. This negative right here is a reflection over the x-axis. If this were plus log base 5 of x plus 2, it wouldn't reflect. And then right here, let's go ahead and underline that and box this. This x plus 2, h is negative 2, so it's a translation left 2. Cool? All right, one more. I'm going to push pause. Here's your first exponent 1, since we practiced them or since we learned about them. First I had to manipulate g of x a little bit. I split up the 3 to the x minus 1 into 3 to the x and 3 to the minus 1. This now flips into a denominator right there. So I got negative 2 over 3 times 3 to the x. I want it to look like this 3 to the x. That's why that 3 stays there. So this negative is a reflection over the x-axis, and then the 2/3 is on the outside. It's a vertical scale, vertical transformation with a scale factor of 2/3. Okay, really hard to see. I tried to, you can sort of see it down here, just a little bit, but super hard to see. cool. 2/3 is just a hard number. If it were a big number, you'd see it really easily, but... All right, and your lesson summary. I really like these general forms, and what the variables do is really, really important. Okay, that was a long one. I know. I'm sorry. Thanks. Good job.